Start, sir.
Okay, so hello students. So today we have our live session 2, and in this live session I'd like to address if you have any queries regarding the course. You know, the course name is Physics of Linear and Nonlinear Optical Waveguides. Okay, so hello students. So today we will go to start the live session 2, which is the second live session. In the last live session, we addressed few questions regarding the course, which is Physics of Linear and Nonlinear Optical Waveguide. So today we will going to address few more questions if you have. So last day we discussed briefly about the course content and discuss few things. Today I like to continue that part as well, unless I get any question from your side. So today I briefly discuss once again about the directional coupler. And the directional coupler, when we study as a optical fiber component, optical fiber based component. And this optical fiber based component actually used in many places, and there are several applications of this optical coupler. We can use these as a switching element, we can use these as a power coupler, we can use this as a WDM. In switching, what we do normally, there are 4 branches and we launch a light in one branches, and we can extract this light to other branches. So this is normally the switching effect we have. Also, for power coupler, we can use this coupler as a power splitter. It can split the total amount of power, and whatever the ratio you want, you can divide this power to that particular ratio. Maybe it is a 50%, 50%, maybe it is a 40%, 60%. So whatever the ratio is required, if I want to split the power, so I have a waveguide where a light is propagating with certain amount of power, and then I need to divide this power into 2 parts. So this 2 part, I can do whatever I need. I can do is a 50-50, I can do is another. And in WDM system, what happened that this is a very interesting application we have, that if we have a system having all different wavelengths that are mixed. So the input light I am having, and in this input light I have 2 or more different wavelengths, they are mixed. So WDM is a system where we can separate out these 2 wavelengths. Whatever the wavelengths are there in one branch, I can divide this wavelength into 2 parts, and 2 different wavelengths can be separated. And this is also a very interesting application, and this is called the wavelength division multiplexing. And in optical communication, we use this kind of component very often. Now the question is, we know the working principle of this kind of optical components, but in this course I put emphasis to understand how this kind of things are happening, really happening. How one can separate out the 2 wavelengths, how one can split the power, how one can use this optical coupler as a switching. These kind of questions are there. We know the principle, working principle. We know that if I launch a light, it can couple and it can go from one waveguide to another waveguide. But the detailed theory that we addressed in this particular course. And in order to understand what is going on in optical coupler, first we need to know what is the couple mode theory. So couple mode theory is an important theory in understanding the fact that when the 2 waveguides waveguides are placed very close to each other, and if you launch a light in one waveguide, then how the light will couple to another waveguide, and you can have the power in other waveguide where we didn't launch the light at all. Well, this couple mode theory, we start from very basics, Maxwell's wave equation, if you remember, and then we have Maxwell's wave equation with a field psi, big psi, and we divide this psi into two parts. One was the mode that is propagating in one waveguide, and another is a mode that is propagating in another waveguide. So it is a combination of these two modes that we call the big psi, which is the total mode. So I launch a light, this light is separated into two waveguides, and individually for two waveguides I write the field, and if I add these two fields, a linear addition of these two fields gives us the total field. That was our initial field distribution, the form of the initial field distribution. Now, next, what we do that we put the propagation constant of these two waves, these two modes that is propagating into two adjacent waveguides. And in one case, if it is a beta 1, in another case, it is a beta 2. And then they are propagating. Okay, so I got one question by that time, a live question, and the question is asked by Pritam Pal, and he is asking about can you please explain Dale operator operation in electric field of pulse propagation inside the nonlinear waveguide. Well, if you go back to the nonlinear pulse propagation problem, so if you remember the way we did this calculation, in that calculation we started with a pulse propagation problem in under Carr effect. First we started under Carr effect. Then we try to understand what happens if there is no dispersion, and we started with our own Maxwell's equation. So we started with the Maxwell's equation, and in this Maxwell's equation, this Dale operator was there. So this Dale operator, it is basically the Delsquare operator rather, because in the Maxwell's wave equation, it should be Delsquare E plus K0 square N square E equal to 0. Helmholtz equation with N having the function of omega and I, because now we are dealing with the nonlinear waveguide. So that's why the refractive index should be a function of intensity as well. That we need to take care in the calculation. Well, then this Delsquare operator, whatever the operator we have, if we calculate in the Cartesian coordinate system, it should be the combination of three coordinates, d2x plus d2y plus d2z. So these three components are there in the system. However, if I consider this operator to optical fiber, then we need to modify this Delsquare operator for the optical fiber having a cylindrical geometry. So now my Delsquare operator should be written in cylindrical. However, in pulse propagation problem in nonlinear waveguides, this Delsquare operator I can separate into two parts, and then these two parts, one is the transverse part and another is the longitudinal part. So this transverse part is associated with the transverse distribution of the mode. If it is XYZ coordinate, then this transverse part should be contained with the X and Y, because these are the transverse component we have, and Z is the propagation direction that is propagating through the fiber perpendicular to X and Z. This operator now will operate over the entire field. And if you go back to the calculation, if you look at the calculation that the way we did in class, Then the total field is considered to be a combination of three parts. One is F, we call F. That F is basically the transverse field distribution. Then we have psi, which is the envelope function. Very, very important, because at the end of the day, we're going to find out what is the envelope equation. And finally, we have the exponential term e to the power of I beta 0 z minus omega 0 t. That was the plane wave term. So there were three terms, and the dependency of these three terms is given also. For example, x, which is a mode which has a transverse distribution, is having a coordinate. It depends on the coordinate x and y. Then we have psi. Psi is the envelope, and we know that envelope is a function of the propagation constant z and t. And then the plane wave part. Now, when this del square operator operate over this entire function, obviously, two parts of this del square operator will operate two parts of this entire function. For example, del square tau, del square t, which is the transverse part of the del square, will go to operate over f, and z square, which is a part of the del square operator, will operate over the psi and the plane wave portion. And then we can make a separation of variable thing. We did it. Separation of variable makes the thing easier, because in separation of variable, what we find that two equations are there. One equation is related to the field, and another equation is related to the envelope. And when the field and envelope are two different equation, because their dependency is different. The field equation is depend on the transverse coordinate x and y, whereas the envelope equation depends on z. So they are equal only when they should be. I mean, when they are equal, they should be equal to each other under the condition that they equal to a constant. And we consider this constant as my propagation constant, and this propagation constant is a corrected propagation constant, because when the wave is propagating inside the medium, it basically changed the medium, and the initial propagation constant will going to change. And then what happened that we considered two equations. In these two equations, we have one equation which we call the envelope equation. And in the envelope equation, we use the slowly varying approximation, because d2 psi dz square is very, very less than d psi dz. The second order derivative is much smaller concept to compared to the first order derivative. And we neglect that. This is called the slowly varying envelope approximation. And then after that, what we do, we carry forward our calculation and eventually get our equation for psi, which is the envelope. So the envelope equation we derive. So this is overall the derivation. So I believe, Preetham, you got your answer. The del square operator here, big del square operator here, is now combination of two parts. One is the transverse part and another is the longitudinal part. I separate the function also in transverse and longitudinal part, and then I allow this operator to operate over the total field. And these things will operate separately, and then you use the separation of variable and you get the result, whatever the result you want. Well, now I get the second question. The second question is from Priyanka Kumari Gupta, and her question is, could you, good evening, sir, she wrote that, good evening, sir, could you answer why these days a lot of research in photonics is focusing on nonlinearity than linearity in waveguide structure? Well, this is not a very technical question, but very interesting question in my opinion. I really appreciate the question, because in research point of view, if you go indeed, you find that the nonlinearity is become very, very important nowadays. So that's why I put a lot of emphasis to bring some sort of essence in our course, so that you understand in nonlinear domain what extra you are getting and why it is interesting. So in the course, I try to put in very basic level the concept of self-phase modulation, the concept of optical soliton. So these concepts are very important because many new kind of applications you can think of previously, which was not possible if you consider only the non-linearity of the waveguide structure. So it is always preferable in general, if I, from the general perspective, we can say that it is always preferable to have a linear waveguide structure, because if I launch something, then all the operation will be linear, and it seems that it should be useful because there is no nonlinearity. That means there is no complex things are there, so it will be very useful for applications. But this is not the case. If I introduce nonlinearity, then many new things will appear. One of the major thing is that if you have a nonlinearity in the system, you can generate new frequencies. There is something called frequency mixing, and in the course, if you read the course, a tiny portion was involved in this frequency generation, which is called a third harmonic generation, because we are dealing with optical fiber, and in optical fiber, the structure is centrosymmetric, and the molecules are centrosymmetric. That's why it only allow the chi3 kind of nonlinearity. And for chi3 kind of nonlinearity, in the calculation, if you go back to the class notes or my lectures, you will find that third order effects will be enhanced, and as a result, we have something called third harmonic generation. Also, you can generate second harmonic, but this is a core subject in nonlinear optics. So what is the meaning of second harmonic and third harmonic? The second harmonic and third harmonic means if you launch a light with a frequency omega, then you can generate a new frequency 2 omega and 3 omega, which is very interesting, because that means you are launching a red light and you are getting something, a blue light. So you can convert the photon in such a way without violating the energy principle, the energy conservation principle, and the momentum conservation principle, and you can indeed generate the blue light out of red light. That is very interesting and exciting. So new frequency you can generate using the nonlinearity of the system. That is the biggest advantage. You can use this for laser different applications, like forming a laser with blue light. Also, nowadays, huge research is going on, something called supercontinuum generation, which is a topic where you launch a light to a very specific kind of structure, optical structure, which is highly nonlinear. We call it photonic crystal fiber. Normally, photonic crystal fiber is a fiber where this kind of effect, like supercontinuum generation and higher harmonic generation, people study more, because this is very useful. Once you make the this photonic crystal of fiber, you don't bother about the nonlinearity, because the effective area is so small in these kind of fibers that it enhances the nonlinearity to many-fold. And as a result, if you launch a light with moderate power, then you can generate different frequency. Not only that, you can generate many frequency. A wide band of frequency one can generate also. This is called supercontinuum generation. So this can happen. This can happen when you use the nonlinearity in the system. Also, one of the major implication of the nonlinearity is formation of optical soliton. This is also a fascinating thing, and in the course we basically have this part as well. And there you can see that in the dispersion, what we find that there is a temporal broadening. But if you incorporate the nonlinearity on top of that, you will find there is a counterbalancing effect. So nonlinearity will go to counterbalance, and this dispersive thing will be counterbalanced by nonlinearity, and at the end of the day, you are getting something very stable, which is called optical soliton. That means there is no temporal broadening, there is no spectral broadening. If you just launch a light, The envelope will not going to change in time or frequency domain. It will propagate as it is. And that is very, very interesting, because as if the wave is propagating without any kind of perturbation. Although it is experiencing dispersion and nonlinearity together. But the correct adjustment of nonlinearity and dispersion can lead to a very stable structure, which is called optical solid. In application point of view, the optical solidon is useful, because if you want to send some information, then this kind of distortion is always there, like we have for dispersion. There is a pulse broadening, and as a result, two waves are if two bits are propagating as the envelope, so there is overlap and you lose the information. But if it is optical solitons, so then you can have a very stable and very pure communication. So in communication point of view, it is also very, very important. So these are few advantages of nonlinear optics, and that's why this nonlinear optics is much in research compared to the linear optics, because most of the phenomena in linear optics is known, but nonlinear optics, there are new phenomena that people still exploring. So that's why in application point of view, people find this is very, very interesting and useful. That's why nonlinearity is now under focus in your photonic research. Well, I believe Priyanka, you got your answer, overview of your whatever you wanted to know from my side. I give you the overview why nonlinearity is important. Now I would like to address the next question asked by Pritam. So he asked, sir, can you please explain how K0 square, N0 square, then psi f exponential I beta 0 z term appears in del square term, appears in del square term, appears in pulse. So I couldn't get your question very clearly, but what I understand that you need to. So you are asking why the K0 square N square term if and these are coming. So first, there are two things. If you go back to your class notes, if you really, so there are two equations. One is Maxwell's wave equations. That is my starting point. And that Maxwell's wave equation will already contain this del square operator. Okay, that is the first part. Second part is it is operating over E. It is operating over E. So I need to form the E, the total electric field. So how the total electric field can be formed? This E you already mentioned in your chat box that it is a function of X, Y, Z, and T. Right? So this E supposed to be a function of space and time, if I like to say in general. So what happened that if I divide this E into two parts, in general three parts, as I already mentioned actually. So one will be containing the coordinate xy, another will be containing the coordinate zt. So the quantity that is containing the coordinate xy is called the spatial distribution, and we define this in terms of f. F is something which is the spatial distribution function of x and y. Well, apart from that, in the electric field, we have two terms also. Another is the envelope term, which we define, I believe in my class note, it is psi, defined by psi, which is a function of z and t. And the equation of psi is important because at the end of the day, we're going to solve the equation for psi. And the plane wave term, that means this is a electric field having an envelope and it is moving forward, so like a plane wave. So we can write is a plane wave solution, and this plane wave term will contain e to the power of I beta 0 z minus omega 0 t. So that is the technique you need to use And you basically, if you put this together, you will find that this operator will operate over these things, and when it operates over E, it will give you something. And also another term is there in the equation, which is k0 square n square E. So that term will be simply k0 square in n square. E you can write at psi f e to the power I beta z equal to 0. By the way, this is not inside the operator. Maybe that creates some kind of confusion to Pritham. You mentioned that how k square n square psi terms appears in del square term. It is not coming. It is not inside the del square term. Del square will operate over E only, and when it operates over E, you can separate it out into two terms. But the third term, which is k0 square n square E, or k0 square n square psi f e to the power I beta z, that is already there in the Maxwell's equation. So please do that once in your hand, and you will really understand why this term is there. It is not inside the del square operator. Mind it. Okay, Pritham, I believe you get your answer. If you have any doubt, you can again write something in the chat box. I will be happy to address your questions or your doubts. But that is the case. If you look carefully to the equation and put these things, you will find that it will not be a part of del square. Rather, it is already there in the equation. Okay, please check it by yourself. Okay, again, I got one question from Priyanka, and I don't know if it's a question or not. She mentioned, thanks a lot, sir. This course and your teaching has provided the knowledge of my research work in photonic crystal. Okay, good. So if you have any, I mean, if this course helps you in your research, then I am really happy to know that even this kind of course, which is meant for MSc level, is helping in the research for the research student. And if you have any queries, any doubts, you can still ask me, and I'm happy to know that this is really helpful for you as well. So that's why I prepared this course in such a way that some sort of advanced level thing should be there, which is very closely associated with to the waveguide theory. Normally in the textbook, in the old textbook rather, this nonlinear part is normally we avoid. But nowadays, these things become very general, and in the course, we have a dedicated thing, and for dedicated courses are there for nonlinear optics. So you can take the nonlinear optics course, and you will find it's very useful. Nonlinear waveguide is a part of that. Nonlinear waveguide is a part of that. Well, another question asked by Pritham, sir, what is the meaning of temporal? Temporal means in time domain. So when, okay, these things, let me explain. So when a light is launched, like laser tick, all of you are aware of this laser pointer. In different presentation, we use the laser pointer. So this laser, when we launch a laser light, then there are two kind of things that is happening together. One is the distribution of this laser light over the space, and another is the time distribution of these things. So you may heard of the term like femtosecond laser, picosecond laser, etc. So that means some sort of terminology like picosecond, femtoseconds are associated with this laser. What is the meaning of that? That means if I launch a laser light, then this laser light has a distribution in time domain. This distribution means we have a pulse, and it is distribution in a time domain. And this distribution of time domain is of the order of femtosecond or picosecond, depending on the quality of the laser or depending on the what kind of laser, So this temporal, the word temporal means what kind of distribution we have in time domain. So that's why it is called temporal or envelope function. So the envelope function, that means the envelope so that is associated with this laser pulse is distributed in time domain. That's why it is called the temporal distribution. Okay, Pritam, I believe you got your answer. If you still have any queries, any doubts, you can write in the chat box. I'll be happy to address you. Previously we were discussing about the optical coupler. So optical coupler is useful, and the couple mode theory. We were discussing about the couple mode theory. In couple mode theory, we start with the Maxwell's wave equation, and we form a psi, and this psi is combination of two psi. One is one waveguide, and another is propagating another waveguide. Only difference is that they are having two different amplitude. One amplitude is A and another amplitude is B. And we derive in detail to find out that how these two amplitude is going to change. So that was our calculation. And during the calculation, we find that there is a coupled equation. We at the end of the day, after doing a lengthy calculation, we find that A and B are related to a very straightforward coupled equation. And if I put certain condition like phase matching is 0, then the coupled equation is rather simpler. Delta beta is there is a term called delta beta. If delta beta is 0, then we saw that this coupled equation is very, very simple. You can decouple that very easily. Even though there is a phase term, you can decouple that. And when you decouple, eventually you find how the amplitude A and B will going to evolve when it is propagating inside these kind of waveguides. These waveguides means these two-channel waveguide, which we call optical coupler. You launch the light in one channel, and the calculation suggests that you are expecting the light in another channel due to the coupling. So this is interesting. All the detailed calculation is provided in the course, and once you do the calculation, it will be very, very clear to you that how the switching effect is there, how the light is going from one waveguide is coming back to other waveguide, or how we can split the total amplitude. If I launch a light with power, say P0, so I can divide this P0 into two parts, P0 divided by 2 plus P0 divided by 2. So 50% power in one coupler and 50% power in another coupler, and we can couple the light. It's a very, very important calculation as far as the coupler is concerned. And also you may remember that this calculation is repeated in the next topic, which is optical fiber bracket. So then this technique we again use. Okay, I got another question again from Pritam Pal, and he mentioned that, sir, when Delsquare operator is operating on the electric field x, y, z, t as per the Maxwell's equation in pulse propagation inside a nonlinear waveguide, where the exponential I omega term 0 goes. So these, okay, so if you, so this term will going to cancel out actually. No. So I mean, yeah, if you put this e to the power I omega 0 term, because in the Maxwell's equation, if you look carefully the Maxwell's equation, the time derivative term is not there anymore, because the time derivative term is already we already take care of this time derivative term, and this time derivative term is not there anymore. So that's why your n square term appears there, because when you make a time derivative term, if you need to go back to a little bit earlier lectures, and in earlier lectures these things has done. So this term is already absorbed. Now e to the power of I omega 0 t, this term is there in E, and if I put this into the equation, this e to the power minus of I omega 0 t will be cancelled out from both the sides. This term will no more there. So in general, E will be in this form because we have a time term here. And in order to write the plane wave, I just write e to the power I b0z minus omega 0 t. So even if you omit this e to the power minus I omega 0 t, you will going to get the same result. Because this e to the power of I omega 0 t will simply cancel out from both the sides. It will not going to be in the operator of Delsquare, because Delsquare is the operator that will operate over space. It is not going to operate over time. And there is no time operator there. There is no d2 dt square term. So e to the power minus omega 0 t or whatever will go to cancel out. Pritam, I hope you understand that. Please look carefully the equation and put by your hand. If you need to do that at least once by your own, and then you readily understand how these things are happening. I hope you get your results, because e to the power I omega 0 t term will simply cancel out from both the sides. It will not be there anymore. Okay, because it is the operator, there is no operator that will do the operate. It is operated already. We use this this operator when we calculate our mode equations or the Helmholtz equations. When you derive this Maxwell's equation, during the derivation of the Maxwell's equation, Maxwell's wave equation rather, if you go back to that portion, very first few lectures, you will find that this e to the power I omega 0, this term will come as minus of omega 0 square, and then some other terms are there, and you can write these things in a different way. Okay, yeah, I hope you got this point. Well, it is almost time. We have hardly 5 minutes, 5 to 10 minutes in our hand. So with this 5 to 10 minutes, I like to address the question from your side. If you are online, if you are if you are listening to this live session, any question if you want, you can ask. Otherwise, I'm going to, because time is already there, I need to switch off. There is no question because there was a question circulated to all the students, and I find there is no question in this set. So that means you understood most of the part of the lecture. That is good from my side. But still, if you have any question, then please ask me. I'm here only to address your questions. It is already 5:43, so I should stop at 5:50 because this is the time limit we are having. And then if you have any question, please tell me. I'm waiting for your question. And the optical coupler thing I already discussed, that couple mode theory is important theory. If you learn the couple mode theory in the problems in optical fibers, then it can be useful to understand the optical bracketting. Optical bracketting is also a very interesting application, very sophisticated kind of application one can think of, like stress sensor or temperature sensor. A huge amount of research is going on till now. People are making optical bracketing in the labs, and that optical bracketings are now used in different places as a sensor. So this we know. And then okay, I got a question. I think this will be my final question. I need to explain that within 6 minutes. And the question is, explain the self-phase modulation and why the name is so. Well, it is very difficult for me to explain that verbally. You need to go back to, you need to check my class note. But I can tell you overall what is the physical significance and why the name is so. Well, the name suggests that it is self-phase modulation. That means if I launch a pulse, this pulse should contain two quantities. One is amplitude and another is phase. So this amplitude and phase, these two terms can be affected by the nonlinearity of the system. And if you go back to my calculations in the course, you will see that if we have a current nonlinearity, only the phase will be affected. So if you launch a light, Amplitude will not going to be affected, but the phase will going to be affected. Very straightforward, the simple calculation is there. I believe I did it. And in that calculation, you can see that the phase will be affected by the nonlinearity. That means if I launch a light and it is containing some kind of phase, during the propagation of the light, it will damage the system, it will modify the atmosphere, its surroundings, atmosphere, and as a result, what happened that its phase will get modified. That means due to the presence of the pulse itself, its phase is modified. That is quite interesting. And you can think of an analogy like suppose you are walking over the muddy road, and there is a structure of the road, but still it is a muddy. If you walk on that particular road, what happened that because of your weight, there is a distortion over this road, right? There will be a distortion in the structure of this road. So that means you are creating the distortion because of your own. Here also the similar thing is happening. If you launch a light, this light will create a nonlinearity. This nonlinearity, because of the since the light is creating this nonlinearity, what happened? This nonlinearity is going to change the refractive index. This change of refractive index will be experienced by the pulse itself, and as a result, its phase will be modulated. So that's why it is called the self-phase modulation. The pulse that is propagating inside the medium create a nonlinearity. Due to the nonlinearity, what happened? The refractive index will get modified. Due to the modification of refractive index, what happened? Its phase will be affected. So at the end of the day, the phase of the pulse will be affected by the nonlinearity, which is created by the pulse itself. That's why it is called the self-phase modulation. I hope, Pritham, you get my point and you understand what is roughly the self-phase modulation. Calculation, as I mentioned, please check my class notes, and it's clearly done that how the self-phase modulation how the nonlinearity is affecting only the phase, not the amplitude of a propagating pulse. So we are almost there, only 2 minutes in my hands. If you have any queries, any question, please ask me quickly. Otherwise, I need to switch off. Any question from anyone who are listening, or any doubts, I'll be happy to address the questions. Yeah, in the last minute we got one question. I think this is the last question I need to address. Pritham asked one question. Can you please explain the centrosymmetric molecule? Well, centrosymmetric molecule is a molecular structure, and this molecular structure is a special kind of symmetry. What kind of symmetry? If a molecule, a point we have x, y, z, and if I have another point minus x minus y minus z, then these two should be identical. The molecule will be distributed in such a way that we have a point of symmetry, and the symmetry point is if we have x, y, z, I have a similar point at minus x, minus y, minus z. So this is called the center of symmetry. And this center of symmetry, if we have a molecule with center of symmetry, then the important thing one can prove that the second order susceptibility will not be there. Not only second order, any odd order susceptibility will not be there. Only the even order, any even order susceptibility is not be there. Only the odd order susceptibility will be there. Silicon, silica, these are few example of centrosymmetric molecules. I strongly suggest you to please type the centrosymmetric molecule and find in the internet that how the molecule will look like. A very, very good pictures are there in the internet, and very nicely they demonstrate how it is centrosymmetric, etc. But in our point, in our course, it is important because the silica through which optical fiber is through which the light is propagating, because the optical fiber is made of mainly silica. This silica is centrosymmetric in nature. This molecule of the silica is centrosymmetric, and as a result, what happened? Chi2 effect is not there in the silica anymore. So in the optical fiber, you don't have any kind of Chi2 effect. We get only the Chi3 effect. That means second harmonic generation, Carl nonlinearity. These kind of effects we're going to find in this kind of system having centrosymmetric molecule or having a center of symmetry. So this is roughly the meaning, and that definitely depending on the arrangement of the molecules. So if the molecules are arranged in such a way in the group theory, if you learn the group theory, then these kind of symmetries are there. So centrosymmetric molecules are such molecules, as I mentioned. If you have a point at x, y, z, another point, identical point, you can think of with minus x, minus y, minus z. That is exactly the mirror, some sort of, it is not exactly the mirror image, it is just the opposite point, and you're going to get something there. And the symmetry is something like that. Yeah, I guess Pritam, you got your answer, and I strongly, as I mentioned, I strongly suggest you can go to the internet and find just type centrosymmetric molecule, and you're going to get very good graphical representation of such molecules, and you will have a clear idea what is going on. Well, I think with this note, I need to end my live session because other professors are waiting for their turns. They also have a live session at 6. So if you don't have any question, then I like to switch off. So I request the persons in IIT Kharagpur to tell me what I need to do to switch off.
Yes, sir, you can. You can.
Okay. Okay, thank you. Thank you. I am leaving right now. Thank you for all the students and all the questions. And the last live session will be there, and we will again discuss if you have any questions. And tentatively it is scheduled on 16th of April. So on that day, we will again discuss this.